All right, in this work example, we're looking at the physics of gravity here. And question 1A reads, explain how a satellite may be in a circular orbit around a planet. The key word here is circular. So I just mentioned a moment ago to the students live in class right now that, I like to say objects don't just move in circles on their own, okay? So in order for something to move in a circle, a centripetal force is required. A centripetal force, which in general is mv squared over r. Centripetal force must act. Okay. This force is provided by gravity. You kind of clean that up a little bit in your own sort of on your own paper. This force is provided by gravity, and the equation for gravity, the force of gravity, is G_m_m over r squared. So as we continue to read through the paper, we're going to have to sort of use those equations coupled with some other ideas to show that there's an expression for the density of the Earth that's given by 3 pi n cubed over gt squared, where t is the time it takes the moon to orbit, and n is the number of Earth radii to get out to the moon's orbit. So if r is the Earth's radius, nr is just how many Earth radii to sort of get out to the moon there. All right, let's work through this, this one here together. We start with centripetal force mv squared over r, but remember for that example, the radius is n times r. It's provided by gravity, given by Newton's law of universal gravitation, G_m_m over, in this case, it's nr squared. All right. We need a few other ideas here to make some substitutions. Note that there's no velocity in this final expression. So we need to think about, well, what really is velocity? It's distance divided by time. The distance of the moon orbiting in a circle is going to be the circumference of a circle. And the circumference of a circle is 2 pi r, but r here is still n. So we have this expression for velocity. We can also make a substitution for mass by considering that density is the mass per volume, right? And the volume of a sphere is 4/3 pi r cubed, right? So this will allow us to get an expression for mass in terms of density and in terms of the radius of the Earth, all right? So we need to put sort of all this alphabet soup together now until we end up with this sort of final expression. So let's just take care that we don't lose track of anything. If we divided both sides by lowercase m, that would effectively cancel this, right? M divided by m is 1, m divided by m is 1, 1 times the rest is all the rest. If we think about what this squared really means, it means nr times another nr. We can just kind of write it like that and then say, oh, if I multiplied both sides by nr, I would cancel out one of those. And so right away, we can see that v squared is equal to g, capital M, the mass of the Earth in this case, over that quantity nr. Here's velocity, and we know that velocity is equal to this. So we're going to plug all of this in here for v and just sort of square everything. And so it is 2 pi n r over t, quantity squared, right? Don't forget to square it, equals, we'll just copy that over there. All right, I'm going to rewrite this up here as 4 pi squared n squared r squared over t squared, equal to, keep the right side the same for now. Now we need to substitute for mass, right? Like I said, we need an expression for mass. There is no capital M in this, and so, but there is a density, right? So we'll rewrite this as the mass equal to rho times 4/3 pi r cubed, right? Just multiplying both sides by the volume. So instead of writing m right here, I'm going to write what it's equal to, rho times 4/3 pi r cubed. So that was just m and g. I still have this nr down here, right? And on this side, I just got everything the same. So far, so good, right? All right, so this r is going to cancel one of those, and then the other two get canceled by these two over here, right? So all the r's go away. Nice, because there's no r in this final expression. So that's why they all sort of cancel away. Now we just got to make rho all by itself, right? We got rho all by itself. And so let's get rid of everything else that's around it over here. I want to divide by g to get rid of that. I want to divide by a 4 to get rid of that. I want to divide by a pi to get rid of that. I want to multiply by a 3n to get rid of those. And those are going to cancel. Pi is going to cancel. G is going to cancel. 4 is going to cancel. So that's the magical factor that eliminates everything on this side of the equation except for rho. So if I do it to this side, the cardinal rule of algebra, right? I got to do it over here. So 3n 4g pi. So multiply all that on this side too. All right, those 4s are going to cancel. This pi will cancel one of those pi's. This n will combine with that n to be n cubed. We got a 3 there. So this side becomes 3, right? N cubed. You still got one of those pi's up there. And then you got a g down here, right? That g stays there. You got your t squared down there. I think that's everything. And then over here, we've got rho. And that resembles that, right? 3 pi n cubed gt squared. Hey, we did it. Well done. 4 marks for that. See, it's a lot to keep track of, but it's sort of just the basic definitions of density, of velocity, the velocity of a circle, right? Going around a circle, we got to know circumference there is the distance. And then just putting all those ideas together, you can eventually get an expression there for density. So that's not too bad once you get to know it, right, YouTube? Leave it down in the comments below. That's probably a good time to hit that like button. Make sure you're on the Dr. Schleich notification squad for all the newest videos for your ACE physics needs. All right, remember that expression, 3n cubed pi over gt squared. It's still on your paper in front of you if you got it. So it's 3 pi n cubed over gt squared, right? That's what we have. And now we need to calculate the actual numerical value. How many kilograms per cubic meter is the density of the Earth? So first they give us the radius of the Earth and they give us the distance between the center of the Earth and the moon. So if we divide this number into that number, we're solving for n, right? It's like saying the entire distance from the Earth to the moon is 3.84 by 10 to the 5 kilometers. And we're saying the radius of the Earth itself is 6.38 by 10 to the 3 kilometers. So what number n do we multiply that by to get the whole distance? In other words, how many Earth radii, how many of these to get out to the moon? So dividing each side by the radius of the Earth there. We realize that n is about, I think it's like 60. 3.84, this is where you need a calculator, right? 3.84 by 10 to the 5 divided by 6.38 by 10 to the 3 is 60.18. It's about 60. The moon is 30 times the Earth diameter away, right? So it's 60 times the Earth radius. That should make sense. All right, so now we've got 3 pi 60, that's the value of n cubed, over, you may recall that g is 6.67 by 10 to the negative 11. And the time, they say, is 27.3 days. It says the period t, or the orbit of the moon about the Earth, is 27.3 days. Days are no good here because the units of g are Newton meters squared per kilogram squared, and a Newton is a kilogram meter per second squared. So we need seconds of time. We need the base units of time, not days. There are 86,400 seconds in a day, right? Because there's 3,600 seconds per hour times 24 hours per day. So 3,006 or 60 times 60 times 24, right? Is this? Or you could just memorize it like I did. 86,400 seconds in a day times 27.3 days gives us a period of 2,358,720 seconds. And we got to square that, right? Because t was squared. All right. Be careful how you type this in. 3 times pi times 60 times 60 times 60 divided by, use grouping symbols for this, 6.67 times 10 raised to the negative 11th. And then, whoops, I messed up. I got to start over. 3 times pi times 60 times 60 times 60 divided by, open parentheses, 6.67 times 10 raised to the negative 11 divided by 2358720 squared equals, I get a final density of 5,486. It's 85.8. And even that is a little bit too precise. You kind of want to think about, there's 3 significant digits in these. And so we should really round this to the, to 3 significant digits. And so let's just call this 5,000. Actually, okay, 5,490 is a pretty good answer. If you want to keep like the 86, I suppose that's fine. I kind of even like this as a better answer, 5,500. That actually agrees with what you may recall from the very similar question that we did with Jupiter. Let's cue that one up and remind ourselves. Oh yeah, we did this one, right? With Io up around Jupiter. And look what it said at the very end. It said, Earth has a mean density of 5.5 by 10 to the 3. And there we've just shown the same thing with this paper. And so in the previous one, you may recall we had to compare sort of the density of Jupiter that we calculated. This answer here was 1,300. To the 5,500, they just sort of tell us and say, oh, that's why Jupiter might be a gas and not a rock, right? Earth is said to be a planet made of rock. Well, we just sort of saw that with this paper here. And so for a final answer, let's just cue it back up. Should have got that. This has been another worked example with Dr. Schleif, and we'll see you next time.